Hello and welcome to another episode from Spiral Physics Education. In this lesson, we're going to be looking at human reaction times, thinking distance, braking distance, the factors that affect thinking and braking distances, stopping distance, and also recapping kinetic energy and braking distance, which was also covered in episode 1H. So check that out if you like to. So what do you need to know to get the most out of this? Well, you should now be able to calculate velocity and speed. Also recapping about velocity time graphs, so calculating acceleration from a velocity time graph and also distance traveled from a velocity time graph. And if you're unsure about how to do any of those, then please do check out some of the other episodes on the channel. So first, let's look at human reaction times. Well, human reaction times are defined as the time that it takes for a human to respond to a stimulus. So in biology, that could be a stimulus for any of the senses. But in terms of driving, it's going to be an audible or a visual stimulus, so something that you see or hear. And in terms of typical values for human reaction times, well, it's really difficult to say what a typical value is because they vary from person to person. And also, they can vary for individual people as well, depending on different factors. But if you are really concentrating just on one thing, you could probably get your reaction down to at best 0.3 of a second, and not much better than that. However, if somebody shouts at you to do something, you're probably going to take 0.6 of a second to react. Sometimes you're asked about how to measure reaction times, and you may have done this in class. So there's one method where you ask a friend to hold a ruler above your hand, and then they let go and you grab it as fast as you can, and the length of the ruler that drops is linked to your reaction time. So the shorter the distance that the ruler drops, the faster your reaction time. So technically that isn't a calculation or a measurement of your direct reaction time, but you could do something like this to see how your reaction time is affected by drinking cups of coffee or Red Bull, or a stimulus, the stimulants, something along those lines. But it doesn't tell you your reaction time as such. But if you know an equation like this one, which if you've done any further maths or looked at any A-level physics specifications, which I'm sure you all do in your spare time, you might come across this. You're not expected to know this for GCSE. But if you do anything with maths beyond GCSE or IGCSE or physics for that matter, you'll come across this equation. And if we rearrange it, we get this. So we could, if we wanted to, and we were doing A-level physics, calculate our reaction time by using just a ruler. So let's say that we drop the ruler and we catch it after it's gone 30 centimeters down, or 0.3 of a meter. We know that gravity is 10 meters per second squared, so we can just chuck those into our equation and we get 0.24 of a second to two significant figures. But that's not really, you're not expected to be able to do that calculation. But so this method isn't a direct measurement of your reaction time. There is a way of doing it though. And you can use a computer with some software installed, or a web-based app perhaps, where there is a visual or an audible stimulus, and noise or something appears, and you're asked to press a button on the keyboard, and the computer directly tells you the time between the stimulus and you pressing the keyboard, and that does tell you what your reaction time is. And they're usually very quick and reliable, and you can do lots of repeats. So that is a very good method of measuring your reaction time. And if you'd like to have a go, go on to humanbenchmark.com and you can have a little bit of fun with your reaction times. Okay, so thinking distance. Well, the definition of thinking distance is quite simply the distance that a vehicle travels while the driver is reacting to a stimulus. And what that means is it's the period of time before the driver is able to put the brakes on. They're just reacting. They've seen something happening, and they're saying, "Oh, I should put the brakes on," and they're in the process of reacting to putting the brakes on. But during that time, because the car has a speed, that car will travel a distance, and it's called thinking distance. And it's all down to the reaction time and the speed of the car. Okay, reaction time of the driver and the speed of the car. Braking distance, well, it's all to do with braking. So it is the distance the vehicle travels while the brakes are being applied until it stops and comes to rest. So those are the two distances that we're going to start looking at, and we're going to do a little bit of an activity. We've got lots of different factors that can affect thinking and braking distance. So we're going to look at all of these different factors and apply them to a Venn diagram, because everybody loves Venn diagrams. So let's think about alcohol. So alcohol affects your reaction times. So that's going to be thinking distance. Speed of the car. Well, if you think about it, it's both of them. Because if your reaction time is 1 second and you are traveling at 10 meters per second, then that 1 second you will travel 10 meters. If you are traveling 20 meters per second and your reaction time is 1 second, you will travel 20 meters. So it's definitely thinking distance. If you are traveling at 10 meters per second, that means you've got kinetic energy. And kinetic energy is a half mv squared. And what brakes do, they get rid of that kinetic energy. So in scientific speak, the kinetic energy store is transferred into thermal energy because the brakes do work, i.e. braking. So when the brakes are applied, they do work on the car's kinetic energy, reducing the kinetic energy of the car. So it's also braking distance. So speed is both thinking and braking distance. Tyres, well, tyres is all about friction on the roads, which is all about braking. So tyre quality is braking distance. Road quality is exactly the same. It's all about friction on the road, so it's about the braking. Mass, well, mass is about kinetic energy, a half mv squared. So remember that the brakes are trying to reduce a half mv squared to 0. So that's all to do with braking, nothing to do with thinking. If you're eating something, you're not fully concentrating on the road, so that's going to affect your thinking distance. Wet road reduces your friction on the road, so it's all to do with braking. Gender has nothing to do with it, so sometimes you do get the odd one like car colour or something like that. It's got nothing to do with either thinking or braking distance. And you might then using mobile phones, that's going to it's going to impede your ability to react quickly. The quality of the brakes is about friction, so it's braking. Icy roads is about friction, so it's about braking. And also drugs. Well, if you do take some drugs, they can increase and also decrease your thinking distance by affecting your reaction times appropriately. So very, very common question about sticking in some factors into those two categories. Students often are convinced that when it snows, people are distracted by it snowing and saying, "Oh, isn't it pretty? It's snowing," but stay away from that. Just don't get into the discussion about the weather affecting your reaction times because you're distracted by it, because usually you don't have the option of arguing your answer in these types of questions. So stick to these answers on the screen, okay? Now we've got stopping distance, and the definition of stopping distance is a very simple mathematical equation. It is thinking plus braking distance, and it is simple as that. You just add the two together. So in exams, well, stopping distance questions usually come up in the guise of a velocity time graph, and it's a very good opportunity to do some synoptic based questions. So here we've got a velocity time graph, meters per second, and time in seconds, and we're going to have a car moving at 15 meters per second, and we're going to have a deer suddenly appear out of nowhere in front of it. So it's not going to be a messy situation. We're going to have the driver reacting in 0.6 of a second, and we're going to have the car decelerating for 3 seconds at a constant rate, and then not hitting the deer, so it's not going to be that messy for the deer. So we're going to try and draw a velocity time graph for that description there. So the car, if we look at it, the car is moving at 15 meters per second. So we're definitely starting up at 15 meters per second, but the reaction time is 0.6. So for for 0.6 of a second, the car is traveling at 15 meters per second. And then it's going to decelerate for a further 3 seconds at a constant rate, and it comes to rest. And that's what that looks like. That's what all of those words put together mean. That graph is going to look like that. Next bit, we're going to calculate the thinking distance. So the thinking distance, well, that's the distance that the car travels while the driver is reacting. But this is a velocity time graph, so we need to realize that the area under a velocity time graph is distance, and the distance that's being asked is this distance here. And that's a rectangle, so we just do 15 times 0.6, which is 9 meters. All right, now let's look at calculating the braking distance. Well, the braking distance is the distance traveled by the car while the brakes are being applied to make it come to rest. Now, distance is still area under the graph, but it's this area here. And I recognize that as a triangle. So we've got half the base times the heights, which is that. Oh, don't know why it's there twice. And if we multiply that out, we get 22.5 meters, and that's the braking distance for the car. All right, so what about calculating the stopping distance and then trying to calculate how far the deer was when the driver first saw it? Well, we know that stopping distance is thinking and braking, and thinking was 9 meters and braking was 22.5. So we've got a total stopping distance of 31.5 meters. Not the end of the question though. The question is how far away was the deer? So we add on another 3 meters to that, and the deer was 34.5 meters away. So that was a slightly synoptic question now. So we're going to calculate the deceleration of the car. So if we think back to other episodes here, we know that acceleration from a velocity time graph is going to be the gradient, and that the gradient is rise over run. And if we look up here, that's the rise. 15 meters per second, or technically it's minus 15 meters per second because it goes from 15 to 0. And it does that in 3 seconds. So the run is 3 seconds. So if we do minus 15 divided by 3, oh, not 0.3, that should be 15 divided by 3. 15 divided by 3, or minus 15 divided by 3 is minus 5, which gives us a deceleration of 5 meters per second squared. So notice that I've taken the minus sign out there because the minus sign is actually telling us that it's decelerating. The speed is getting smaller. So that's how you calculate the deceleration from a velocity time graph. So other questions that you can get, and they get quite complicated now, is linking braking distance and kinetic energy. So this is covered in episode 1H in far more detail. So do have a look at that. I'm just going to touch on it here just to give you a reminder of it. So let's say that a car has 200,000 joules of kinetic energy store, and that its brakes exert an average force of 3,500 newtons to bring it to rest. And we're going to calculate the braking distance to 2 significant figures. So one thing that we need to realize is that the change in the kinetic energy of the car is going to be work done. And because it's mechanical work, mechanical transfer, that's force times distance. So that's the force exerted by the brakes times by the distance that the car is traveling while the brakes are applied. So that means that we've got decrease in kinetic energy equals force times distance. And if we rearrange that, we get change in kinetic energy over force for our braking distance. And now we can just bang in those numbers and we get 57 meters to 2 significant figures. So the thing to remember here is that when a car brakes, we've got kinetic energy store of the car, and the whole thing about the brakes, what they do is they transfer the kinetic energy store to the surroundings, maybe a little bit of sound, but mostly thermal energy store of the surroundings increases. And that's what the brakes do. The brakes are doing work, and that work is the change in the kinetic energy of the car. So it's all down to the equation work is force times distance, and also kinetic energy being half mv squared. So if you're unsure about those two concepts, do check out other videos on the channel about work, energy, and kinetic energy. And just so that you remember, the decrease in kinetic energy is equal to the mechanical work done by the brakes, i.e. mathematically, it's this. And that delta means change. So the change in the kinetic energy of the car, or the decrease in kinetic energy of the car, is equal to force times distance. So sometimes the exam boards like to tap into something that you guys probably will have to do when you learn to drive, and that's look at the highway code. And this highway code, you are expected to know thinking distances and braking distances for certain speeds. So this graphic here is something that you will become very familiar with should you wish to pass your theory driving test. And it just shows how thinking and braking varies with speed. So just ignore that circle for the moment. What we're going to ask is, I've seen it come up a couple of times in exams over the past, and it says, what's the relationship between thinking distance and speed? And this is a common question in physics. We're looking at relationships between two sets of numbers. So we're going to be looking at speed and the blue arrows, just to summarize that. So if we start here, we look at 20 miles per hour, and we're going to see if there's a relationship between these numbers and the distances. So if I choose a nice number to go with 20, and 40 is quite a nice number because that's an increase of 2. And then I look at the two numbers that are linked to those speeds, and those numbers, the distances, go up by a factor of 2. So if speed increases by a factor of 2, thinking distance increases by a factor of 2. But is that the same for all of the different data that's represented here? So let's have a look at a different set of data. So let's stay with 20, and looking at it, 60 is a nice number because that's an increase of 3. And if we look at the distances or thinking distances associated with that, 6 to 18 is also an increase of 3. So in response to this answer, one thing that you could say to get 1 mark in an exam is, as speed increases, thinking distance increases. And that's 100% true. That's worth a mark. And then you've got to try and get a more complicated mark in that they are directly proportional because both increase by the same factor. If speed increases by a factor of 2, thinking distance increases by a factor of 2. And I would always advise you to quote the data. So say 20 to 40 miles per hour, thinking distance increases from 6 to 12. And then you could also do it from 20 to 60, which shows an increase of 6 meters to 18 meters. And that's directly proportional. So another question could be, what about braking distance and speed? Again, just ignore that black circle for the moment. It's out of sequence. So let's start with looking at 20 miles per hour again, and we'll go up to 40 because that's a nice number. That's an increase of a factor of 2. And if we look at the braking distance, that goes from 6 to 24, which is an increase of 4. So it's not quite the same relationship, and you can see that by the length of the arrows. The red arrows on there increase by a greater amount each time than the blue ones. So let's have a look at another set of data to see what happens with those. Let's ignore that black circle for the moment. So let's go from 20 miles. Distance is proportional to v squared. And that means that the relationship's not proportional because the factors aren't the same. One goes up by a factor of 3, the other one goes up by a factor of 9, one goes up by a factor of 2, the other one goes up by a factor of 4. What if speed increased by a factor of 5 though? How would braking distance increase? Or going by that sort of relationship that we looked at before, braking distance would increase by a factor of 25. And that's because work done, force times distance, is equal to half mv squared, or the change in kinetic energy. And that means that the distance is proportional to v squared. And this is why that slogan says speed kills. As you can see there, that the greater the speed, the greater the stopping distance. Each stopping distance increases significantly when the speed increases. And that's because not only does thinking distance increase, that's proportional increase, but braking distance increases far more than thinking distance. When thinking distance doubles, braking distance quadruples. So per hour to 60, because that's a nice increase of a factor of 3. And if we look at the braking distance, that goes from 6 to 55, and 6 to 55 is an increase of factor of 9. So doubling the speed causes the braking distance to increase by a factor of 4. Trebling the speed causes the braking distance